Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can implement rotate right using structural design first in Verilog, and then we are going to do that in VHDL. So this is a Verilog program first, and here I have designed a module which is rotate right, and it has one output and two inputs, and all are of 8 bits. And after that, I have shown here three code lines. So the way these code lines work is I can show you that we can implement actually the same rotate right in behavioral design like this as well. So in this always block, what we are doing is we are saying that if the first three bits of the input B are 0, so then don't rotate, just give the values of A to the output S. So since A is of 8 bits, so we need only first 3 bits of B to do the all combinations of our rotation for 8 bits. And then we are going to say, okay, once B is going to be B2 to 0, 3 bits are going to be 1, then we are going to say rotate towards right by 1. So this is the way we can implement all this. This is slicing and concatenation we are using here, and this is the way up to rotate 7 we can rotate all bits, and then we are going to say else this one make s equal to these. So what we are doing here using this behavioral design is actually we are going to convert this behavioral design into a structural design, and that's where I am trying to modify this code, and these three simple lines are doing what these 8 if else statements are doing above. So with this behavioral code, what we are doing here is we are trying to first use this s1 to shift by 1, and we are going to say check the value of b0. If it is going to be 0, just give a as it is to s1, don't rotate by any bit. But then we are going to check that if b0 is going to be 1, then rotate a by 1 and give that to s1. So this is what actually we are doing here as well for 0 and 1. So here first bit is 0, here first bit is 1, and after that we are going to say okay, now do rotate by 2 bits, and for that what we are going to say is we are going to use this s1 not a right now, and then we are going to say now if b second bit which is b1 is going to be 0, give s1 as it is to s2, right? And if b1 is going to be 1, we are going to say rotate s1 by 2 bits and then give that to s2. So this is the way we are going to implement two shifts, and these s1 and s2 are now going to give us these first four combinations because we have checked first bit as well and then the second bit as well. And now comes the third bit, and the third bit we are going to use here. We are going to say now if third bit b2 is going to be 0, just give s2 as it is to the output s. But we are going to say then that if b2 is going to be 1, then rotate s2 by 4 bits and then give that to output. And this is the way using these a s1 and s2 we are going to combine all these 8 operations. So this is actually right now a behavioral model, and with these code lines I am going to implement later the structural model as well. But first we are going to do the simulation and see its output. So go to test bench. Actually, let me show you the test bench as well, the way we have written. So this is the module test bench. In another file, we are defining here output S as wire, and we are going to define here the two inputs as reg, the way we usually do it. And here we are calling that rotate right module, which we have designed in the other file. And then during this initial block, we are going to say at 0 time make A and B as 0 0, and then after 10 nanoseconds we are going to say start this for loop, and then we are going to increase the values of A by 4 and the values of B by 1, like B starts from 0, 1 2 3 4 5 6 7, all the rotate combinations we are going to see. And then after that for loop we are going to again give our A and B inputs some values so that we can try some other combination as well. And this is the complete program of our test bench. Now I am going to simulate this test bench. So first we are going to see this output, which is going to show our both input signals and the corresponding output as well. And later we are going to check that during the structural design the output is same. So this is going to be the output. So we can see here the 4 after rotating towards the right side by 1, it is going to become 2, and same way these all values. And now I am going to change this code to a structural design code. So if we look at this is actually a mux, this is also a mux, this third line is also a mux. So we can implement all these three lines by using a mux. So outside this module we are going to create a mux. So let's uncomment these lines. This is our mux, 2 to 1 mux, which is 8 bits. It has also 8-bit output and two 8-bit inputs, one select line which is 1 bit, and here we are saying check select signal. So if our select signal is going to be 0, give input 0 to the output, and if select signal is 1, give input 1 to the output. And same logic is here. So we are going to actually skip out these lines and include for this line, this line. This is our mux. We are calling here, and then we are going to give this A to the input 0. This rotated A by 1 bit to input 1 here, and then B0 to the select line, this B0, and then S1 to the output of our mux. And then we are going to skip out this line. We are going to use the same mux again here, and now we are going to give this B1 to the select and S2 to the output here, and then S1 to the input 0, and then the rotate right by 2 bits, which we are going to get from here. We are going to place it here, and same way we are going to skip out these lines, and we are going to implement this line with a mux as well. So this is our structural design. Structural design is once we are going to use the mux as a component, to design this rotate right logic. So this is our complete program. Now let's try to save and compile this. So compile is successful. Let's simulate this. Run this, and we are going to see the same output. So this is our rotate right using Verilog language. And now we are going to actually flip over to our VHDL project, and we are going to see how we can implement rotate right using a structural design in VHDL. So this is our VHDL design file, and here we have defined an entity which is rotate right, which is again of 8 bits. So its output is vector of 8 bits, input also 8 bits, two inputs also 8 bits. And in the architecture, we have again given these three code lines, and the way they are working is they are going to work the same way the way these if else statements are working in this process block. And here we are doing the same thing. We are going to check the first three bits of our input B, which is going to tell us that rotate towards the right side by these many bits, like 00, just don't rotate. 001, rotate by 1 bit, and then 010, rotate by 2 bits. So same logic we are going to apply here, and we are going to use only three code lines. So these three code lines, the S1, S2, and S, are going to give us the same logic which these 8 if else statements are giving above. This is the way actually the rotate right logic we can implement. Now let's compile this design and see its output too using simulations. So go to Testbench, run, and we are going to see this output, which is going to show us the two input signals A and B, their values, and then the output as according to those values. Now let's end this simulation and try to implement this behavioral design in VHDL using the structural design. So what we are going to do is we are going to first of all create an entity which is going to give us the mux, and this mux is also going to be 2 to 1 mux, which is going to be an 8 bit. And in this architecture, under this begin block, we are going to say if select is going to be 1, then give the input 1 to the output, otherwise give the input 0 to the output. Same logic we are going to see in our design code as well. So here we are going to use the above entity as a component inside our architecture of the rotate right. And now we are going to use this mux. And first of all, we are going to skip this line, implement this line using the mux. Then we are going to skip this line, implement this line using the mux. And then we are going to skip this line and implement this line using the mux. The same pattern our code has. Save, compile this code. So now our VHDL design using the structural modeling is also ready. And now we are going to actually simulate this using Testbench. So I am going to show you actually the Testbench of VHDL as well. So this is going to be our Testbench entity Testbench, and then in the architecture of that Testbench we are going to call this component rotate right, and then we are going to call this entity rotate right in our begin block like this as well, and we are going to map the inputs and outputs according to these signals. And then we are going to start the process block, and here we are going to first set up our two inputs as zeros, and then we are going to wait for 10 nanoseconds, and after 10 nanoseconds we are going to start this for loop, and after the end of this for loop we are going to give two more inputs to our a and b, and then we are going to end this process and end this architecture. So this is our test bench on the same pattern the way we defined the test bench of our Verilog design. Simulate, add all the signals to our wave window and run simulation. So we are going to see the same output according to our two inputs. So this is the complete design using the VHDL language as well. So thank you guys. I hope you guys have enjoyed this video. Have fun.